So what we can say is, I mean, right, I am just writing a little bit loosely here in the sense that, okay, this is small z, okay. So if I have homogeneous coordinates and I want to go back to my heterogeneous, I just have to scale by this last guy, that z, right. If I want my original xy, I am still calling this as xy, if you want you can call this x dash y dash, but that is okay. Right. You know that if I wanted to get back to my image coordinate, I just have to scale by this z, right, and this is equal to, see, for example, right, I mean, see, I'm going to write this in terms of a matrix, a 3 cross 3 first to start with. Okay, this is the simplest camera intrinsics that you can have. 0 f 0 0 0 1 followed by, okay, so see, this is 3 cross 3. I'm going to follow it up with a 3 cross 4 matrix, which is 0 1 0 0 0 0 1 0, and this matrix, its importance will I mean, right now, okay, well, its role is this x, what is that, what did you say, xc, yc, zc 1, right. So the same thing, when you want to express the 3D coordinate in terms of its homogeneous form, xc, yc, zc 1, right. So you got this as 4 cross 1, this is 3 cross 4, this is 3 cross 3, right. So effectively you will get 3 cross 1, right, on the left, and if you multiply these two, right, you get xc, yc, zc, and then here, right, you have f 0 0 0 f 0 0 0 1. This in turn will give you fxc, fyc and zc, right, which then means that small x equal to f times xc, small y is equal to f times yc, and small z is equal to zc, right. And I know that if I want to go back to the original image coordinate, I just have to simply scale this by zc. If I scale this by zc, I kind of get back my, that is a small z, right. I just have to scale it and I get back my, say, original image point, right. So if I scale x by z, y by z, small z, okay, is my say image coordinate, right. Huh. Huh? No, small z is not f. Small z is simply this representation of the, say, 2D coordinate in terms of its homogeneous form, and that will be equal to capital ZC, because you have to scale by that, right. I mean, you have fxc and you have to scale that by zc to get your small x.
Not able to get what is small z.
See, the
Small y or the image point?
no, you need to get your small x and small y. Okay, here, I mean, okay, that's why I said it. If you want to think about it, think of this as x dash y dash. Okay, and you want to go, so it's like saying that, I mean, I have my say original coordinates as x comma y. This is my image coordinate, right. I want to transform into this, say, homogeneous form. The general homogeneous form is x dash y dash, let's say z dash, where I will express my x as x dash by z dash. I will express my y as y dash by say z dash. Now the question is, what should be the small z dash and what should be my x dash and y dash, right? And those have to be related to the camera parameters, because everything finally boils down to what the camera is doing, right? So, and we know that eventually we want this equation, no, which is actually, I mean, this is the one that's happening on the image plane, right? Fxc by zc is what is happening. Now y is fyc by zc, right? That's what you want. And therefore, the only way you can write it is this way. I mean, but there's a reason to write it, because, right, this portion, we will see later how to extend this, okay, and this portion is the camera. Right now it's looking simple, right, it just has a focal length, but we will actually make it a little more interesting. Okay, so then fxc by zc, so therefore, right, yeah, I mean, if you want it, you can write this x dash y dash z dash and say that, right, xy is x dash, so x is x dash by z dash, and if you want, you can even think about it, it does not matter, y dash by z dash, but in general you just write it as x y z, right, with the understanding that you have to scale by the last coordinate, right. Okay, now the point is, see, right here, one of the assumptions, okay, that we made is this. See, for example, right, we assumed that, I mean, I have not drawn it exactly, but then the assumption is that the center, let me draw it by a different color. So this center, which is the optical center, right, it exactly coincides with the center of this image plane. I mean, here I have not drawn it like that, but it's like saying that, right, I have my image plane and this optical axis, right, that is actually passing through it, this center and right and this center are exactly aligned. That means the center of the image plane. But it could happen that they are actually not aligned. That means this guy could be off a little bit. I mean, this is all a manufacturing thing. We are assuming that it's all perfect, right? But then, okay, right, it need not be. So there could be a small shift here, but that's a kind of a permanent shift. It's a manufacturing thing, right? And to accommodate that, what we do is we actually use that offset, right, that might be there. If it is there, you have to account for it. If it is not there, not a problem. Then it will be, so that offset, right, we actually call that, let's say, Px and Py, okay. So let's say that the camera offset, these are things that can actually happen, okay, and they do happen. That's why you need camera calibration. Because, right, that's also the reason why you do a camera calibration, because if you don't calibrate a camera, that means if you don't worry about what the intrinsics are and simply go ahead and do some triangulation and all, you will go wrong, because the actual place where it is imaging, right, you have to express it correctly, right. If this matrix is not correct, then all your calculations are going wrong, okay. So you have to account for them. So that's camera calibration. So the camera offset, let's say, right, is given by, suppose we say that the camera offset is given by, what is this, what did I say, Px comma Py. That means the x offset is Px, y offset is Py, okay. Then the way to accommodate that is to actually throw that into this k, okay. So let's put that into this. So okay, this is an intrinsic parameter, right. So f0, so it comes here. It does not come anywhere else, it is a part of the camera. Just as focal length is a part of the camera, then you have 0 f, then you have Py, then you have 0 0 1. Okay, now, if you notice, right, if you again multiply the right hand side, that 3 cross 4 or 4 cross 1, you still have xc, yc, zc, right, and therefore if you multiply the 2, you get like fxc plus px zc fyc plus py zc, and then you have zc, right. So again, if I want my image coordinate, I should do fxc plus px zc by zc, but fxc by zc is my original x, and px zc by zc goes away, so I get x plus px, and similarly fyc plus py zc by zc, right, will give me y plus py, which is what you want, right. So you want to account for that px and py, okay. If there is a manufacturing thing, right, that's a manufacturing stuff, okay, but that has to be accounted for. And during camera calibration, these are the things that you actually find out, and these are frozen, right. For a camera, this is fixed, okay, you don't have to keep changing it. So the intrinsics once and for all, if you calibrate, it's kind of fixed. This f itself, right, looks like right, that is okay. No, you can just keep it like that, but actually even there, right, there's a little bit of adjustment needed. Okay, there is something called the field of view, right. I mean, you've all heard about field of view of a camera, field of view, right. We keep saying field of view, right. That field of view depends on this f and the sensor dimensions. Okay, so for example, okay, if you think about the sensor, okay, now let's say, right, we have something like this. Okay, let's say I have a width w and then I have a height h. Okay, this is the sensor. Okay, this could be in millimeters or something, right. Now what we are saying is that right, we have the optical center, right, going through this. Let's assume that there is no drift or anything. Okay, just going through the center. And now if you actually look at this ray, right, that's I mean, if you look at this outermost ray that kind of hits the top of the sensor and goes, and if you could have look at the bottommost ray that also hits. So for example, if you look at this line and then look at that cone that's going, right, that gives you the field of view, right. So this angle, right, if you think about this as theta, then the field of view is actually 2 times this angle theta. Okay, that's your field of view. And right, simple thing will kind of show that so if I do tan of theta, okay, so this theta is of course half the field of view. Okay, the full field of view is 2 theta. So tan theta is w by 2, okay, because this height by f, right, because from here to here is f, from the camera center or the optical center to the image plane center, that's f. Oh, sorry, h by 2, yeah, h by 2. h by 2. So, it is h by 2f. Therefore, ref looks like what is this, h by 2 tan theta. Right, I mean h by 2 tan theta. And similarly for the other one, right, if that field of view, okay, so for that, right, what will you have, and if it so happens that h is not equal to w, it can happen, right, you can have a sensor which is not square, right, I mean here we have taken a general sensor, so for that you may have w by 2 tan phi, which means that your field of view along the height is not the same as the field of view along the width. It can happen, which generally does not happen, but yeah, most general case you can take h naught to be equal to w. Okay. But then what happens is, even if h is equal to w, right, there is still a small sort of a problem that can arise, because if you look at this, right, theta is after all an angle, so tan theta is no units. But look at h and w, right, so they are in actually millimeters or something, right, you have a sensor of some 2 millimeters by 2 millimeters, something you will have, or 1 inch by 1 inch, right. Now, so this f turns out that f will also be in terms of inches or millimeters or something. But if you actually look at the xy coordinates, right, that you have, there is a small x and a small y, we actually typically represent them in terms of a pixel location, right. We don't say x is 0.01 millimeter from the center, right, we want it in terms of the coordinate, right, and therefore, and also at px and py, either you can express it in terms of, you can do, there is nothing wrong. For example, the intrinsic camera matrix can be expressed entirely in terms of just what do you call, in terms of the actual length, okay, but then that is not normally done, right. Pixels are more useful, because otherwise every time you will have to do this conversion. If I say 1 millimeter, then you have to worry about a 1 millimeter, how many pixels, right, does that contain then, and so on. So normally we would like the camera, that intrinsic matrix, to be such that if I just use it, then it will tell me where the point is, and not like I have to do a conversion after that. Okay, that's the normal thing. So now this f, if you look at it, right, this h, even if let us say, right, even if okay, right, it does not really matter whether h is equal to w or if not, but then the point is, what could matter is, if I have what do you say, I mean, so for example, right, I mean, if I kind of look at the density, the density of these pixels, right, see, I mean, I can have a sensor which is perfectly square, okay, this square, let us say, right, I have HH, assume that I have a square sensor, but what can happen is, right, I may have a density like this. I mean, again, right, this is all, it may not happen, but then, right, I could have something like this. That means for the same length, right, along one direction I have, let us say, right, 3 pixels, but along the other direction I have got like whatever, right, 9 pixels or something. It can happen. I mean, you may have a camera that has like 496 by something, 1024, even though the sensor size is probably a square. Okay, that means that your density is actually varying across, across x and y, it is not the same. So when we write that f and f, right, and you know that the second f is actually multiplying for the y coordinate. The first f has an influence on the x coordinate, right, in that matrix, that k. See this guy that had that f0 0 f0, right, 0 0 1. So this f is kind of responsible for the y. This f is actually responsible for the x, and if the pixel density is not the same, then that has to be accounted for, right. And therefore, what is normally done is we write this as alpha f. If alpha is 1, then it means that the pixel density is the same, but if alpha could be less than 1, could be more than 1. If alpha is different, right, then it means that your pixel density is actually not the same, and therefore should be accounted for when you do this conversion. Is it okay? So a more general form, right, then is like this, right. So the intrinsics now changes to f. Some people write this as fx and fy, but actually it simply means that, and then they will say there is an aspect ratio between the two. It is all one and the same, but the simplest way to understand is in terms of this one, density. So f, then 0 px, 0 alpha f, py 0 0 1. Alpha, if it is higher along that axis, along y.
Along y axis, alpha will be greater.
alpha, if alpha is greater than 1, that means along y axis you have a higher density.
So the final coordinate will be alpha f yc by.
Correct, correct.
So it will get.
So it will get scaled by alpha, not added, scaled. Okay, now see there is one other thing, okay, which can also happen. That is like, one of the assumptions which we are making is that this is exactly, each of these pixels is actually a square or actually a perfect sort of a rectangle, right? We are sort of assuming that this angle is actually 90. Okay, that means it's like they're exactly orthogonal to each other. But then we saw some operation, right, earlier. What was that operation which could actually turn something which was actually perpendicular to something else, shear, right? So what can happen is sometimes, right, this need not be exactly orthogonal. I mean, you could have some little bit of angle between them. They may not be 90. It could be like not be exactly 90. So to account for that, right? So this parameter here, this is turned into shear S. Okay, so this is like your shear. I mean, if you want to think about it, but then this is about non, what do you call, orthogonal. This is to account for orthogonality. This is for non orthogonality. This is for pixel density, and this is for the offset. So in that sense, right, you've got like 1, 2, 3, 4, 5 unknowns. Okay, and in a most general K, which is the camera intrinsics, this is called the camera intrinsic matrix. Called the camera intrinsic matrix, and the most general form that it can take is this. And one other thing that you observe is what? Something else which is interesting about this camera.
Upper triangle.
Exactly, upper triangular, and there's one more thing. If it is just upper triangular, maybe it's not so interesting. With all non-zero diagonal elements, which means what? Which means that it's always, right, invertible. You can always invert this guy. Okay, so this matrix is upper triangular, non-zero diagonal elements, okay, invertible. Okay, this is as far as the camera matrix K is concerned. So which is why you can freely use K inverse and all. You don't want to go from, right, want to do any inverse operations and all, you can comfortably do that. Now let's kind of talk about this extrinsics.
So what is the name you give to alpha?
Which one?
What is the name you give to alpha?
What is the name we give to alpha? I don't think we give any name, just a factor there.
No, so you wrote something.
Oh, no, I just said pixel density.
Oh, pixel density.
Represents the density. I mean, I don't think they have a name for that. Even for S, right, they don't explicitly say it's a shear, but that's what it is supposed to encapsulate. Camera extrinsics. So, right, I mean, all this, okay, right, we are actually doing because, right, eventually what we want to do is, for example, when we move to stereo, right, we will have, let's say, one camera here, and then we may have another camera here. It could be that it's the same camera that we have shifted, or it could be that we have actually two cameras, right, on a rig, and we have a point here, right. So unless we know, for example, how to kind of say represent the coordinate of this point in this camera frame, and how to actually, right, represent this point in this camera frame, then when we want to search for a correspondence, or we want to know, for example, right, if you know the correspondence, how the triangulation should be done and so on, then we should know where this point goes here, right. So it's like saying that right, I mean, if this point is here and if that point goes there, then we should be able to express through a projection matrix what will happen to this point if it is, right, I mean, if it falls on this image plane, and what will happen to this point if it falls on this image plane, and if the cameras are not the same, then how should you account for that? Because it need not be the same camera, right, it can be a different camera. That means the K could change, and in all such cases, and also right, there could be a relative rotation and translation between these two cameras. I mean, that's when you get a stereo, right? Pure stereo is like pure translation on the on the image plane. That's the purest stereo. But yeah, you can have a general stereo where you have an R and T, and therefore, right. So the intrinsics and the extrinsics together come now in order to be able to tell what's happening, and that will actually decide. So for example, right, I mean, so for example, if I ask you, right, suppose I am able to tell, right, where this point comes here. Okay, now this point, I mean, so it's like saying if I get a back project, right, I have the optical center here, I have an image point. If I do a back projection, right, it goes all the way, that ray. I know that my 3D point is somewhere in that ray, but I should be able to. Now suppose I ask where is this point, right, on this image plane. We should be able to tell, right, whether is that lying on a curve on this image plane, is that lying on a line on this image plane, is that where is it going, right? So such things when we want to, so for example, if I want to say where does this line map to on this image plane, I should be able to tell where it is, so that then I can search on that line for my coordinate sort of a correspondence. I mean, if I don't know the correspondence, if I know the correspondence, then you can triangulate and so on. But all of that requires this extrinsics and intrinsics. Before the without that we cannot do any of this. So we have to be able to express the scene coordinate in terms of the image coordinate. Whatever you may have n number of cameras, then you will have n number of intrinsics and that many extrinsics, because each camera is kind of positioned somewhere, and you want to know what is that R and T. Okay, so we are doing this exactly for that reason. Okay, all right. So the extrinsics, right? It will be like this. So to go to the extrinsics, okay. So see, until now, right, what we said was I have a coordinate system, right, that is actually centered at the optical center. Okay, so YC, and then this is my optical axis aligned with this is my ZC aligned with the optical axis, right. So here is my, let's say, the camera center C. Okay, now what could happen is somebody could kind of have a world reference which could be aligned in some other direction. Let's say this is XW, this is a world coordinate system centered here, and this is YW, and that is some ZW. Okay, and this person gives you the coordinate of this point in 3D, okay, which is what we are interested in, but then our camera is somewhere. So it's like this, right. So if he gives you the coordinate of this point with respect to XW, YW, let's say ZW, right, with respect to, okay, this coordinate system, whatever, right, let's call this as O, okay, this is, or let's say CW or something, right, if you want to, okay, let me call this CW. So this is like a world coordinate system which is centered somewhere else. Okay, this is a world coordinate system with respect to which I know this. Now the point is, right, see, we know kind of how to write, I mean, how to say where this point will map on this image camera plane if this coordinate was expressed in terms of the camera coordinate system that we just now saw, right. If you tell me that it is XC, YC, ZC, I know where it will map, but now you are not telling me in terms of this coordinate system, you are actually giving me in terms of another coordinate system. Now you might ask, why would somebody do that? The whole point is this, right, like I said here, if you had another camera sitting somewhere else, right, with respect to, then you need to be able to relate the same point with respect to this coordinate system and with respect to the other coordinate system, right. That's when you can actually tie things up. The same point seen from there, seen from here. So the world coordinate typically, even when we do the calibration and all that, we typically tend to use some coordinate system which is convenient, and we will call it the world. That is the way. So this is still single view, by the way, right. I am not even talking about two view, but I am just trying to motivate this two view from here. But this is all still single view. I have one camera, and we are still doing only what we can do with respect to expressing the coordinates. And all that we are saying is, can I express the image coordinates given that the world coordinate is not with respect to the camera coordinate system, but with respect to a different coordinate system, which could be a world coordinate system arbitrarily chosen. Okay, so all that we are still doing is all single view. Okay, single view geometry. This is all single view. Okay, but then you see, remember that is exactly these ideas that will come back when we do a two view geometry, or when we go to see multi-view geometry. Okay, now for example, so the point is, right, I have this point P here, right, and okay, let's go. Okay, now so now, right, what we know is, okay, now this is the, okay, now the C is the coordinate Now I have written that as C. Okay, let us say that it is actually a vector. Okay, C is the coordinate of the camera center or the optical center with respect to CW or with respect to the world coordinate system. Okay, so with respect to this coordinate system, this guy is at some C bar. Okay, and this point is here. Okay, so kind of one way to kind of think about it is, okay, so kind of one way to think about it is, I mean, if you call this as xw vector, that is xw, yw, zw, then one way to think about it is you kind of account for this say translation that exists between the two, in the sense that you can do say xw minus c bar, right, because actually, right, this guy is at c bar, it is not at say cw. So one way to think about it is you do an x bar w or this vector minus c bar. Okay, that will be like, that will be, but then right, that by itself will not solve the problem, because if you do just that and if you try to plot that point, right, with respect to, okay, where this xw minus c bar will go, right, it may not exactly give you the same point, because it may go somewhere there unless you rotate, because these two have a mutual rotation also, right. If it was a pure translation, I could have simply done this, right, and I am there, but then because this could be differently rotated, so unless you kind of do a rotation, account for the rotation, you cannot kind of come back to this, so this, so the coordinate of this point with respect to the camera coordinate system will be some xc, yc, zc, right, that is equal to xw minus c rotated. So it is like translate first and then kind of say rotate. So translate first and then you say rotate. You can also rotate first and translate. You can do both, but in this case it's like translate first, translate and then you say rotate. Then a rotate. So what this means is, if this point is plotted, this will exactly hit here. It should give you the same point P. It should not give you something else. Okay, so what this means is that, so let us call this as xc, right, a vector xc which represents xc, yc, zc. So we have xc, right, is equal to r times xw minus c. Okay. Now let us again go to the say homogeneous coordinates, because finally, right, we want to go back to that equation, right, where we had this 3 cross 4 matrices and all. Therefore, what we can do is, let us call x tilde, xc tilde to be the homogeneous representation of xc, and x tilde w to be the homogeneous representation of xw. Okay. So now this is 4 cross 1, this is also 4 cross 1, right, and then what this means is that now see earlier, right, what we had like x, y, z, right, is equal to whatever that K matrix, which is the most in its most general form. Then we had 1 0 0 0 0 1 0 0 0 0 1 0, and then I had here xc, yc, zc, right, this is what I had. No, zc1, yeah, correct, zc1. Okay, now which means that this is my xc, okay, tilde that I have there. Now we know from the previous expression that xc tilde, okay, now so now see, if I have instead of x, no, where is that? So here, right, if in the previous one, if I convert this into say xc tilde, and I want to write it in terms of xw tilde, see this is xc yc relation, right, xc, yeah, by the way, xc xw relation, right, but then I want to kind of express it in terms of the homogeneous coordinates. Then what you can do is you can actually express that as k, right, into, okay, now this one, right, we typically partition it as identity and then partition as 0, where 0 is a 3 cross 1 vector, I is 3 cross 3. Okay, that is a short form, instead of keeping on writing 1 0 0 and all, right. So you have I comma I dash 0, and then okay, this portion, right, that we want will look like this. So we have r and then minus rc, okay, and 0 which is a vector, 1 and then what is this, x w tilde. You can actually show this. I mean, you can easily show. Okay, this is 1 cross 3 by the way. R is 3 cross 3 and this one is minus RC and the last one is a scalar, that is just 1. So, this is actually 4 cross 4. This is 4 cross 1. This is 3 cross 4. This is 3 cross 3. This 0 vector, okay, is 1 cross 3. Okay, and then this can be further simplified. So, you can actually multiply these two matrices and that will give you K. Okay, now yeah, so one of the things that we will do here is that we will call this a projection matrix, okay, this guy. So, it is like saying I have the world coordinate of that 3D point with respect to some world coordinate system, that is my x tilde w, and I want to find out where it maps in my image plane when my camera is somewhere else, okay, which is what we said is this C, right. C is where the camera is with respect to that world coordinate system. So, in order to get it there, by taking into account the camera intrinsics and the camera extrinsics, right. So, this is called the camera projection matrix or simply a projection matrix. And always right, remember that a projection matrix relates 3D coordinate to the image coordinate. Homography is always between two image coordinates. Okay, this is not a homography, this is a projection matrix. It tells you where does a 3D point map on the image plane. Okay, so, the projection matrix gives you where it goes in my image plane. A homography is between images, okay, there is no 3D camera projection matrix, right, called P. So, this is a standard, this is not that point P, okay, this is that matrix projection, maybe I am just using P because that is the most common thing, and then K. Now, if you multiply these two, right, you will get R minus RC, and then this will be like 3 cross 4, this will be 3 cross 3, and therefore, P is always a 3 cross 4 matrix, a camera projection matrix. This is the world coordinate, and all of this is in the homogeneous form. Okay, so, we act on a 4 cross 1 vector, which is your 3D world coordinate appended with 1. The projection matrix acts on it, gives you 3 cross 1 vector, scale the first two by the last one, you get your. Okay. The other way to write it is, there are different forms for this. You can actually pull this R out because it is common, and then you can write this as I then minus C. Okay, you can also write like this. And this sometimes, right, this also can be kind of written as K, and then sometimes this is written as R slash T, where T is a translational vector 3 cross 1, and then the interpretation here is, right, you see this P is going to act on your this one x tilde w, right. So, if you look at this, what would you interpret this as? Yeah, exactly, right. So, it is like rotate first then translate. If you look at this form, it is like translate first then rotate. Okay, so, and both forms are okay. This is like rotate, first rotate, then translate. And this is like first translate, then a rotate. Okay, whatever be it, but then the most standard form is this. Okay, RT, because it is very clear. So, it has the intrinsic camera matrix, which is K, and then this is your extrinsic camera matrix, extrinsic camera matrix. It has only extrinsic parameters, no? So, it has how many unknowns now? This extrinsic has 6, 3 rotations, 3 translations, right? All in, of course, you see 3D. And K has 5 unknowns. And how many elements does P have? Actually, it has 12, 3 cross 4, right? It has 12 elements sitting in it, but then we can only estimate it up to a scale factor, right, because of this homogeneous coordinates, all derived with respect to homogeneous coordinates. Therefore, P itself can actually compute it only up to a scale factor and there are 11 entries there, and actually you have actually 11 unknowns. 5 is sitting in K and 6 sitting in the extrinsics. Right. So, P by the way can be found only up to a scale factor. Up to a scale factor. So, in that sense it has actually 11 degrees or no, yeah. So, basically right 11 unknowns. Degree of freedom is slightly more tricky. I mean, I won't use that. Let's say 11 unknowns, because for example, right, R has actually 9 elements in it, but do you have 9 unknowns? The degrees of freedom is only 3. Similarly, translation of course it's 3. So that way the degree of freedom and unknowns is it's not they are not the same. Okay. So then what this means is that any time somebody gives you and say a 3D point, you should be able to simply apply the camera projection matrix to get your X. In fact, right, sometime maybe I'll show you maybe one example of one of my students is working on this ball tracking and all. So we are doing something in this indoor, what is that, some room, okay, where we have set up cameras and all. So you can actually see, right, and how you can track the 3D point of the ball using 2 cameras, right. All this goes in there. Okay, so we have to use, so we have to do the camera calibration, we have to know K, right, we have to know everything in order to be able to tell where the ball center is, right, and so on. So actually all of this, I mean, one can actually take it up as a lab thing and then do it. Okay, I mean, if you are interested, right, you could also do that.